Welcome everyone to this presentation of the paper Low-Layer Functional Split Management in 5G and Beyond, Architecture and Self-Adaptation. My name is David Campoy. I am one of the authors of this paper and also member of Universitat Politècnica Catalunya. And I am going to present you this project that we did in the context of a European project called Verge. So I would like to start with some of the identified trends for beyond 5G and 6G cellular systems, which are the following. There are many, but we identified the key ones, which are diverse and challenging requirements for new services. This can be low latency services, high reliability services, or high throughput. We also saw the Open Run proposal for a disaggregated and softwareized run. And finally, we also saw a trend for a centralization of some baseband functions towards data processing centers. These baseband functions can be OFDMA processing, channel coding, digital modulation, or channel estimation, to mention some. So having all this in mind, we identified new opportunities for a flexible deployment and intelligent network management. Okay, so now I would like to explain the concept of flexible functional split, which is the following. So looking at the figure, at the left part, we find the core network, which is connected with the RAN by the backhaul link. Then the RAN is split between a cloud or edge side, which we will call the BBH, baseband high, and the far edge side, which is close to the antenna, which we are going to call BBL. So these two places are connected with a front haul link. So below you can see that all the baseband functions that we have to be executed in order to process our signal can be executed either at the BBH, at the BBL, or can be executed in a distributed manner. So some of them can be carried at the BBL and some at the BBH. This is the so-called flexible functional split, and there is a clear trade-off in the degree of centralization, since with higher centralization we get higher coordination gains, but we require higher bandwidth at the front haul. What we're going to study is a dynamic functional split, which is the change of this split based on traffic conditions or service quality requirements. So in summary, the presented work will focus on a framework to manage these splits, in particular the ones related with the physical layer. Here I will present the self-adaptive split selection application, which we call SASA, framework, which is responsible of the dynamic management of the baseband split between the BBH and the BBL, based on factors such as load demand, user density, or services. So this SASA application manages a 5G RAN composed in general of multiple sites, and each site includes a number of sectors, each one with one or more 5G near radio cells, operating over a certain frequency and bandwidth. The computing resources are split between the BBH resources and the BBL resources. These BBH resources are residing at a central location, and these BBL resources are close to the antenna where the data is generated, and both are executing fee layer functions. Then the front haul network interconnects the different sites with the central location that hosts the BBH resources. It includes a unit that multiplexes the front haul information from the different sectors of a site, referred to as site switch unit, SXU, and a unit that multiplexes the front haul information coming from a different sites, referred to central switch unit, CXU. And SXU and CXU are interconnected by means of a front haul link with a certain capacity. Then this application, the SASA, will make decisions on the selected functional split to use in a cell of a sector or site, and will use monitoring information from the BBH, the BBL, and the front haul network interfaces and configuration parameters of each cell. Based on the high-level representation of the SASA seen before, this is a possible implementation aligned with the Open RAN architecture. As I mentioned before, this SASA framework, the application, addresses the low-layer functional splits, which involves the baseband functionalities hosted at the distributed unit. In Open RAN terminology, this is the ODU, which is managed through the O1 interface, and the RU, the radio unit, managed through the ODU and the Open Fronthaul M-Plane interfaces. Then we also have the Open RAN network functions that can be implemented as virtualized network functions. And the support of virtualization in the Open RAN architecture is enabled by a cloud computing platform called the OCloud. Following on this architecture, we find the Service Management and Orchestration, the SMO system, on top of the Open RAN architecture, which manages the RAN functions and the cloud. And within the SMO, we find the SASA functions that can be implemented as an application, for instance, as an R app in Open RAN terminology, and also the ODU, the RU, and Fronthaul element management systems, which provide management functionalities that, for instance, they are used for performance management counters to be exploited by these SASA functions when making decisions. These performance management counters can be, for instance, the uplink and downlink traffic and fronthaul occupation in the fronthaul link. Finally, the network function virtualization, management and orchestration, the NFV and MANO, enforces the decisions made by the application to select the desired split, let's say. Let's focus now on the optimization target, and at the right part of the slide you can see a figure containing all the baseband functions that we are considering and the splits at the bottom, defined as split 8, 7A, 7B, 7C, 7D, and 6. And for instance, split 8 means that we are centralizing all the baseband functions towards the BBH. So let's go now and comment on the optimization parameters, and which we will start with vector X, which is the vector with the selected splits for each of the sectors in a cell site. So for instance, if you have one site with 5 sectors, vector X will have 5 elements. Then we have CBBH and CBBL, which depends on X, the selected splits, which are the computational requirements at the BBH and at the BBL. Then we define epsilon, which will be greater than 1. This is the ratio between the energy cost at the BBL and the corresponding cost at the BBH. And note that the cost at the BBL will be in general higher than at the BBH. Then we define the maximum bandwidth at the fronthaul link, which is our fronthaul maximum, measured in gigabits per second, and then the required fronthaul bandwidth, which depends on the selected splits, in the downlink and at the uplink. So now, on the optimization problem, we want to minimize this expression, so we want to select the combination, the vector X that minimizes the computational requirements at the BBH and at the BBL. And note that the computational requirements at the BBL are weighted by the epsilon factor. And this expression is subject to the following constraints, which are that the selected split, the fronthaul requirements at the downlink and at the uplink must be lower than the maximum bandwidth allowed in the fronthaul link. Now, about the evaluation scenario in which we are going to do this optimization, it consists of one site with 3 sectors, each one with running a 5G new radio cell. And at the right part, we can see these parameters that we used in the simulation. Then the maximum bandwidth at the fronthaul will be 40 gigabits per second. And then to fill the numbers in the computational requirements and fronthaul requirements, we will use a model that we developed in a paper published last year, and you can check this reference below. So finally, we consider that the traffic load in the different sectors varies a long time, and this application, this SASA, intends to optimize the selected functional split at each time for each one of the sectors. So you can see here in the figure, in the x-axis you have the time of the day, and this load, split it in the three sectors. So for instance, from 8 to 10, we have a 84% load in the first sector and 8% load in the second and third sectors. And this 84% represents the load with respect to the maximum load in this sector. So you can see here throughout the day, this load changes in the total, in the aggregated load, and also the split of the load within the site between the three sectors. Now, focusing on the results obtained, the first figure shows the optimal functional split per sector as a function of the aggregate site load. So you can see here in the x-axis, you have the time of the day, and then the aggregate site load on the y-axis. And this is the same plot that we saw in the previous slide, but I added the optimal functional split for each sector. And what we can see is that the optimum split varies for each sector depending on its load. And also in a general view, we can see that low loads tend to use split 7b, while higher loads tend to use split 7c. That's expected since the energy cost of the BBL is larger than the cost at the BBH. So it is beneficial to centralize functions to the BBH by using lower splits, such as 7B. However, these splits increase the required front-haul bandwidth, so they may not be always fulfill the constraints, and thus 7C, the split 7C, may be needed in some cases. Then the next figure shows the optimum split energy cost in the different periods of the day, measured in giga operations per second. And we see that actually this line follows the same pattern as the aggregate site load. This is also expected since an increase in traffic is directly related to an increase in computational load, as the baseband functions are executed on a per symbol, on a per physical resource block occupied. So an increase in traffic is directly related to an increase in computations. So as you can see here, the optimum energy cost follows a similar pattern like the aggregate site load. And as I said, an increase in traffic is directly related to an increase in computational load. This figure here shows the difference with respect to the optimum when using fixed splits, a fixed split strategy, let's say, for all the sectors and during all the day. This means that we are avoiding this flexible functional split management, and we are selecting the same split for all the sectors and during all the day. So what we can see is that split 7C is only optimum between 4 p.m. and 10 p.m. But between 8 and 10 a.m. we have a 15% degradation with respect to the optimum found before. And regarding the fixed splits 7D and 6, the difference with respect to the optimum are larger, varying between 20 and 25%, where many of the most computational demanding functions are remaining at the BBL. Now, to finish with the results, we can see here two figures that represent the front-haul occupation in uplink and downlink for the fixed split strategies, and also the flexible one is shown. And also the limit, the 40 gigabits per second, is indicated as a reference. What we can see from this, what we can infer from these figures, is that there is a high sensitivity to front-haul requirements for split 7B. If we focus, for instance, in the downlink, we can see that these front-haul requirements escalate rapidly from 30 gigabits per second to 300. So as a result, the use of this split in all the sectors is only feasible during the first period between 8 hours and 10 hours. We can also see that split 7C is always feasible. It always complies with the front-haul requirements. And regarding split 7D or 6, they have a low front-haul utilization. So this adaptive strategy uses as much bandwidth as possible. So for instance, between 10 a.m. and 4 p.m. and between 10 p.m. and 12 a.m., split 7B can be used in one or two sectors, increasing this front-haul utilization. Now, to conclude this presentation, we can state that the presented work has focused on an architectural framework for self-adaptation of the functional split on a per-cell basis, aligned with the Open Run architecture. The proposed application is assumed to be part of the management and orchestration system and collects measurements from the available interfaces and nodes, the distributed unit, the radio unit, the O1, and the front-haul end plane interfaces. As a summary of the benefits in using a self-adaptive approach, we can say that we have achieved energy reductions between 4 and 25% with respect to using a fixed split strategy. This means we are not optimizing this split decision. And also we have seen a better utilization of the front-haul capacity of the system. Thank you so much for your attention, and if you have any questions, feel free to contact us.